Southern Plains Transportation Center, we would like to actually welcome you all, for taking your time this, hot Tuesday afternoon, to join this important webinar. So I think this is, as many of you, and I see a lot of actually known names on the screen. Many of you have participated in SPTC webinar before. So as you all know, that you are all going to get 1 hour of PDH, from SPTC. So if you do not receive your PDH that is given by mail, please let us know, and we'll make sure that you receive one. Also the presentation will be posted on the SPTC website as a file. It's so if you need any other information, of course you can always contact Professor Volz about this particular seminar. But we are really glad that you are able to make it. So if you kindly keep your keep muted, and I think the presentation will be sort of uninterrupted. And please post your questions in the chat box directed to me, Musharraf Zaman. So I will actually ask those questions on your behalf after the presentation is over. You could also unmute yourself and ask questions after the presentation is over. So that way, I think we have allocated enough time. There will be plenty of times to answer all your questions. And as I said, I'm confident that Jeff would answer questions even outside of this as well. Again, we want to thank you all. We know that you have a choice, and this is one thing that SPTC is going to do fairly regularly, probably more regular than we have done in the past. So if you want to see anyone actually that you'd like to see present on a topic, we simply need to know the topic that you want to address, and also the potential speaker. It does not have to be, it could be anyone. Now, not only from this country, it could be from another country as well. That is, I guess, the beauty of COVID. That's what we are all seeing, the significant presence online. So I'm thankful to Dr. Syed Ashik Ali for actually his assistance with the logistics. So with that, then I am going to actually introduce our speaker, Professor Jeff Volz. He is going to, today's topic is innovative multi-hazard resistant bridge columns for accelerated bridge construction. Accelerated bridge construction, abbreviated ABC. University of Oklahoma is a member of the ABC UTC that is led by Florida International University under Professor Etorod Azizi Namini. So you all, I think many of you know Jeff. Dr. Volz is an associate director for undergraduate studies and the director of the Donald Fierce Structural Engineering Lab. We call Fierce Lab, that we are proud of. And he's also the Lloyd and Joyce Austin Presidential Professor within the School of Civil Engineering and Environmental Science at OU. He's a licensed structural engineer and a professional engineer with over 16 years of industry experience. That's really, for a faculty member, that is a significant track record, including 8 years working for the Portland Cement Association. During his 20 plus years of academic career, he has performed research on high volume fly ash concrete, I think. Then he also worked on the self-consolidated concrete, ultra high performance concrete, and fiber reinforced concrete. He is really an expert in this area. He holds 2 patents for cementitious based material for developing and testing. So I think, and this topic is also very important, because this hazard, as you see that with the climate change and everything that is going on, this is multi-hazard is a very important topic. And of course, we all know the importance of bridge. And bridges could not be built without concrete, Jeff, I believe, at least for now. Maybe in future, there might be other options. So with that, the floor is yours, Jeff, and again, I want to thank you on behalf of SPTC and on behalf of our participants of this webinar. So please proceed.
Let me share my screen. Everybody hear me well? I should say, Mushraf, can you hear me well?
Yes.
Good. Okay. So let me get sure this technology gets started here. Okay. Okay. So thank you very much for that wonderful introduction, Mushraf, and I appreciate the opportunity to present this seminar today. Again, my name is Jeff Volz, and the title of my seminar is Innovative Multi-Hazard Resistant Bridge Columns for Accelerated Bridge Construction. I want to focus on a couple of those words first, and the first one, as Mushraf had mentioned, multi-hazard. When we talk about hazards with regard to our structures, we're talking about either natural or man-made loadings on our structures that are often hard to predict, both in terms of intensity and duration and frequency. And so we're talking about things like earthquakes, storm surge, high winds from hurricanes in coastal regions, high winds from tornadoes in the Midwest, vehicular impact for an overpass, barge and boat impact for a bridge crossing, flooding for a bridge crossing. Now, what these all have in common is they place a large load on the structure that's dynamic in nature, and they are not as predictable as we would want. Things like live load on a bridge, we feel very comfortable in terms of the traffic and the trucks, even if you have the occasional overload, we feel pretty comfortable with that. But having to predict the future with regard to these hazards can get very complicated. And I want you to keep in mind that because these hazards cause a dynamic loading on our structure, the issue of ductility and resilience is particularly important and something I'll talk about today. Multi-hazards are where we can have a structure subjected to these different kind of hazards either at the same time or rather close together or even far apart, but we may not have recognized the damage from the first loading condition. And so we have a structure that already has some deficiencies. And as Mushraf had mentioned, this is becoming a bigger issue. The other word was accelerated bridge construction, or other words. We've begun to recognize that the indirect costs from major construction projects in our transportation sector have indirect costs of up to 10 times the direct costs. We recognize that it's worthwhile to spend more money on the initial design and construction if we can reduce how long that construction takes because of the impact on the traveling public and the disruption to our traveling public and the resultant impact on both our state economies and the nation's economy. So those are the two important things I want you to hold on to as we move forward. So in terms of what I'm going to cover, I'll discuss the evolution of the concept that led to the column that I'm going to talk about today. Specifically talk about hollow core reinforced concrete columns and studies on those and why they evolved. Concrete filled tube columns, either steel or FRP tubes filled with concrete, and both of them eventually leading to this double tube concrete fill system that I'm going to talk about today. Based on that column, I'm going to talk about some ways to design it. It's still in its infancy, so we're still developing methods to accurately predict this behavior, but we have some ways to come up with some initial sizing guidelines, sort of where to begin. As we all know, design is an iterative process and we don't know where we are until we get there. And then we're going to talk about sectional analysis. So how do we determine the axial and flexural capacity for these columns? And then I'll discuss a research project that is funded by the Oklahoma Department of Transportation and a companion project funded by the ABC-UTC at Florida International. We'll talk about the specimen design and fabrication, the testing and the results today, and next steps in that research project. And then I'll have a number of thank yous because this project would not have been possible without a lot of people's help, and then answer any questions that you might have. So typical bridge piers will often consist of reinforced concrete columns, often circular reinforced concrete columns, because it's a very efficient method, relatively cost effective. Reinforced concrete has shown to have a high amount of ductility for some of these hazard conditions. But there are some downsides, not the least of which is the weight of these structures. So there have been attempts to reduce the weight of bridge columns, to increase the speed of erection and construction of these columns. And so we'll talk about all of those and how they impacted our current column. Now I'm going to talk about hollow core concrete columns, reinforced concrete columns, and concrete filled tube columns. Now I have to talk about these sequentially, but in truth, these two concepts evolved in parallel and then eventually came together in the concept I'm going to talk about today. So in terms of visualizing how these actually relate, even though I'll start with hollow core concrete columns and then move on to the concrete filled tube columns. But all of that came together in the system that we are talking about today. So in particularly tall bridge piers or areas of high seismicity, engineers have looked at reducing the weight of our piers. We all understand that the columns are more efficient if we can get the material as far away from the neutral axis as possible. That increases the buckling resistance and increases the flexural resistance for less material. Now this requires more formwork. You have to formwork on the inside and the outside of the column. And often to get the best performance, you need two layers of steel that are tied together as you would have in a typical reinforced concrete column. The reason that you need the inner and the outer layer tied together is because of the hollow core. The bars can buckle inward or outward, so you need both of them. But building that reinforcing cage is costly. The other reason is if you have the potential for precasting these columns, you can reduce the weight of them to make them less costly for shipping and easier to erect. Now, these columns are often tested in a constant axial load, increasing lateral load capacity. Basically, the typical specimen is a cantilever. It's fixed at the base, which is what our columns behave a lot in most of our bridge piers, fixed at the foundation and a cantilever extending upwards. They're tested with a constant axial load and a increasing lateral load based on certain loading protocols. And you see the load displacement behavior in the diagram on the right. One of the important things to notice there is that those values up in the upper right-hand quadrant, that 2, 4, 6, and 8 mu, that is the drift ratio or ductility factor expressed as a percentage. So if you have a 10-foot tall column and it can displace up to 12 inches, then you have a ductility ratio of 10 or 10%. So you can see for this column, it behaves very well in its lateral loading. This is a typical hysteresis loop. It's important to recognize that the area within the hysteresis loop is energy absorption, which helps us in these dynamic hazards that can impact our structures. So the more consistent and without degradation hysteresis loop we have, the better behavior. We see that this reinforced concrete hollow core column is behaving very well, up to a ductility ratio of 8%. But that reinforcing cage takes a lot of manpower to build because of having to tie it together. And researchers have looked at the opportunity of using round columns, circular columns that are also hollow, with a single layer of longitudinal steel with a spiral around the outside. And then they've tested those in a similar manner under a constant axial load and increasing lateral load. And you can see in this low deflection plot, the ductility is not as good. You can see we get up to a ductility ratio of about 3%. After that, we get significant failure of the column. And that's because although the bars can't buckle outward because of the lateral tie, you only have the thickness of the concrete, which of course is poor in tension on the inside, and eventually the bars will buckle inward. So that's why it doesn't have as high a ductility ratio as that square column we looked at. Separate from hollow core concrete columns, we built a lot of steel-filled concrete columns. They have been used in the US. They are used very frequently in Europe and in Japan, where you use a steel tube that will also act as a stay-in-place form, which is filled with concrete to form your column. Now, the great thing about this is you've eliminated the need for building a reinforcing cage, which is a significant time save. The steel tube acts as a stay-in-place form, so there's no formwork to erect and then remove, and it goes relatively rapidly. And this has been used in a number of instances. It has a very good performance. If we look at the load deflection plot, same kind of specimen, fixed at the base, constant axial load, increasing lateral load, we get a very good hysteresis loop. It is a very stable hysteresis loop, which is important. And the column has reached a ductility ratio or drift ratio of 6% before it failed. Now, it's not just that we keep that low deflection from degrading. We want basically as big an area within that hysteresis loop as possible, because that is energy absorption during a dynamic loading effect. And the more energy you absorb, the lower the resultant forces on the structure and the more durable it is in terms of strength. One of the problems, though, with these types of columns is we have to protect the steel from corrosion. Right? Steel is at a higher energy state, and because of that, it wants to return naturally to a lower energy state in the presence of moisture and oxygen, and so it will rust. So we have to paint them either with epoxy-based paints, other types of paints to try and protect them, particularly in areas where we use a lot of road salt, because that will cause deterioration of the steel. It'll start to corrode. And our piers, our bridge piers, the columns, if you have an overpass, are right in the splash zone, where that's actually the worst you can have, where you have that constant wetting, drying, wetting, drying with chlorides will cause it to corrode. So that's one of the downsides. But still, it performs very well in terms of its ability to absorb energy. There have also been some developments with, instead of using that steel tube, which can corrode, we instead use fiber reinforced polymer tubes that we fill with concrete. These actually evolved out of some of the initial applications of FRP in transportation infrastructure, which was to repair damaged existing infrastructure. And one of the first applications was actually to wrap circular reinforced concrete columns that have either partially deteriorated or in seismic regions, if it was an older design, to increase the resistance of the column. That wrapping of the FRP will help protect it from external deleterious materials and also provide confinement to the concrete, which will increase its energy absorption ability. So researchers and DOT officials decided, well, why don't we just build new columns with FRP tubes filled with concrete? That eliminates the problem we have with the steel-filled columns and gives us a more durable structure. Unfortunately, testing of those columns shows that they don't have as good an energy absorption. That's primarily because FRP is a very linear elastic material up until failure. So it doesn't have the ability to yield like steel does and absorb energy. You still get some nonlinear performance, so you do get a hysteresis loop that has some energy absorbing ability, but because of the behavior of the FRP, there's not as much area, there's not as much energy absorption and not as much ductility, and the column example on the right failed at about a ductility ratio or drift ratio of 3%. But still an important performance improvement with regard to durability, but like all things, they have advantages and disadvantages, and so you don't have as much energy absorption capability, and therefore the ability to resist these hazards. So the idea for the column I'm going to talk about today sort of melds the best parts of those hollow core concrete columns, reinforced concrete columns, and steel and FRP filled concrete columns, and puts them together in a new system, which consists of an inner steel tube, an outer FRP tube, and then sandwiched in between is a concrete core. So no reinforcing cage. We've eliminated the reinforcing cage and the cost and manpower to do that. We have the steel tube, which provides the ductility and energy absorption ability for the column. We have an FRP tube on the outside, which protects the inner steel tube. Both it and the concrete together help protect the inner steel tube. The inner and the outer tubes act as stay-in-place forms, so there's no formwork. And both of those tubes also provide a high degree of confinement to the concrete. As you know, when you test concrete in compression, and we call it a uniaxial compressive strength, our F'(C) values, that column, that cylinder actually doesn't fail in compression. It failed due to the tension strains perpendicular to the compressive load. And if you had a loading system that had almost no friction at the loading heads, instead of getting the typical conical failures, you would get a series of vertical cracks when that concrete fails. The idea that if you take a ball of concrete and drop it into the deepest part of the ocean, it will never fail in compression because it's under a high hydrostatic pressure in compression. And so it really can't fail. And you can get astronomically high compressive stresses. That's the same application here where the inner steel tube and the outer FRP tube provide confinement to the concrete. So it has a much higher apparent strength than its uniaxial compressive strength. In terms of how you would construct these columns for your bridge pier, first would excavate for the foundation. In this case, I show it as a drilled shaft. Place the steel tube into the foundation, and it could be a drilled shaft or it could be a spread footing. Place the concrete in the foundation that then anchors the steel tube. Drop the FRP tube over the top, and then fill the annular space between the steel tube and the FRP tube with concrete. Then once you have a number of piers, a number of columns, you can then erect the pier cap, form that, and add the reinforcement. Theoretically, you could construct these columns in as little as 2 days. Once you place the steel tube into the foundation, place the concrete for the foundation on that day. The next day, you can drop the FRP tube into place, pour the concrete at the annular space, and the column's done. No formwork, no reinforcing cage, and very much accelerated bridge construction. Once you have all of the columns for a pier, then you can form the bridge cap and pour that. In terms of how we can actually size these columns, there are some guidelines that are being developed and continue to be refined. First, you have to select an initial diameter for the column, and you can use typical column diameters for reinforced concrete as a starting point. And again, design is an iterative approach. We don't know what the answer is until we know the answer. So there is always necessarily some iteration. As more and more of these designs occur, we start to get a better feeling for where to start at. The concrete wall thickness is between 10 and 15% of the overall diameter. So if you have an 18-inch diameter column, then you have between 1.8 and 3.6 inch thick concrete section. The steel tube diameter is simply the outer diameter minus twice the thickness. And then the thickness of the steel tube is between 1/64th and 1/32nd of the diameter of the steel tube. At the lower end, 1/64th of the diameter, you have the tendency for more frequent or more common buckling of the steel tube. At the thicker end, that would tend to eliminate some of the buckling, but it increases the cost and increases the weight. It's important to recognize that the benefit of that concrete core is it reduces the tendency of that steel tube to buckle and the FRP tube to buckle. And we'll talk about that during our actual test. So again, all three of these materials help each other. The steel and the FRP act as stay-in-place forms. The steel provides the ductility, the FRP provides the protection and the durability. They provide confinement to the concrete, and the concrete prevents local buckling and global buckling of the steel tube. And then the FRP thickness is a function of the diameter of the FRP and the ratio of the compressive strength of the concrete, the 28-day uniaxial compressive strength, and the hoop tension capacity, F sub T, of the FRP. And if you're in a low seismic region where you're not going to have as high of strains during one of these hazards, there's a 3.5% for the thickness. And if you're in a high seismic region, such as California or Japan, then you're up to 10.5% of that ratio. And again, these are just guidelines to get you close so that you can then do a more detailed analysis. So then we would do a sectional analysis, which is very similar to how we analyze reinforced concrete columns or steel composite columns. We discretize or segment the cross-section into a series of strips. Because it's a circular column, you need smaller strips than if it was a rectangular or square column. And then we perform a nonlinear strain compatibility analysis, which is exactly what we do for reinforced concrete. We assume a neutral axis location, and then based on plane sections remaining plane, the Navier-Bernoulli beam theory, we can calculate the strains at each level, at each layer, based on its distance from the neutral axis, because the strain diagram is simply linear. Once you have those strains, you go to the stress strain diagram for the concrete and the steel and calculate the resultant stress. From the stress and the area of our strip, you have a force, and then you sum those forces around the plastic neutral axis to calculate the axial load and moment that would cause that strain distribution. From those, you can generate an interaction diagram, just like we would generate an interaction diagram for reinforced concrete. Or if you're looking for a specific moment in axial load, then you'd have to iterate to that solution. Typical assumptions, again, are plane sections remain plane. The power of that is that the strain diagram is linear. We assume a perfect bond between the steel and the concrete. That's the strain compatibility part. Where the concrete touches the steel, they both undergo the exact same strain. There's no slippage. We can use an elastic, perfectly plastic stress strain diagram for the steel, where we have linear stress strain behavior up until yield and then a plateau. We can also make it more refined by including strain hardening if we would want to. We use a stress strain diagram for confined concrete, and there are guidelines on how to convert the stress strain diagram for unconfined concrete to that for the confined concrete based on the degree of confinement that the steel and the FRP provides for the concrete. We typically ignore the tensile strength of the concrete, and we also ignore the longitudinal capacity of the FRP. The FRP runs from the top of the footing to the underside of the pier cap. So it does not provide longitudinal resistance. It only provides circumferential or hoops resistance to the concrete trying to expand when it's placed under compression. It provides confinement as well as protecting the inner steel tube and the concrete from deleterious materials. Just excuse me for a second, I'm going to take a quick drink. And I want to talk about our research project. Again, this research project was funded by the Oklahoma Department of Transportation and a companion project funded by the ABC-UTC at Florida International. So the diagram on the right shows a typical specimen construction for the cyclic testing of columns. This is a very typical one. It's the same specimen type used for the hollow core rectangular and circular columns and for the steel filled, concrete filled steel tubes and FRP tubes. It consists of a base or a footing. The column is fixed at that point, so it extends out of the footing. And then at the top, we place a loading stub where we can apply the lateral load and a constant axial load. Now, these columns that I'm talking about today go by the acronym HCFCS, which simply stands for hollow core FRP concrete steel columns. We also designed, fabricated, and tested a reinforced concrete column for comparison, which I'll talk more about in a minute. Our column we selected in terms of what would work in our lab, we have a column height of 8 feet. That's from the top of the footing to the application point of the cyclic lateral load. The FRP outer diameter, we're essentially testing half scale columns. And we wanted to be in the range of 18 to 24 inches. We chose 18 inches, and because of standard sizes, that gave us an FRP pipe or tube of 18 5/8 of an inch diameter and a thickness of 3/16 of an inch. That is the lower bound value. So that's the low seismicity equation for determining the thickness. The reason we chose that is because we wanted to ensure that we got the materials to fail. If we oversized them and they never failed, no matter how far we pushed it, we wouldn't know what the true capacity was. So we're at the lower end of that for this initial testing. The steel tube has a diameter of 12 3/4 of an inch and a thickness of 1/4 inch. And that's also on the lower bound. That is the 1/64th of the diameter. So you have a higher tendency for buckling as opposed to a thicker one. But again, that concrete core is going to provide a significant amount of buckling resistance to the steel tube. And then the resulting concrete wall thickness is 2 3/4 of an inch. In terms of material parameters, the FRP tube is glass fiber reinforced polymers, commonly referred to as fiberglass. The fibers are glass, and the polymer can be either epoxy or other types. It has a 40 KSI hoop tensile strength. That's fairly typical and is a minimum value for this application. And that's a critical design parameter because that FRP provides the confinement. That concrete wants to expand when it's under compression, and by confining it, you get a much higher apparent strength. The steel tube is an API 5L-X52, which has a yield strength of 52 KSI and an ultimate tensile strength of 66 KSI. That is very close to an ASTM A500 grade C steel. The API designation is very common in the oil and gas industry, which is what is readily available in the state of Oklahoma. But again, it's very close to an ASTM A500 grade C. The concrete core, this is where we're pushing this concept farther in our research project. Previous testing has placed a very normal 6,000, 5,000 PSI concrete in the core. We're examining high strength self-consolidating concrete with a compressive strength of 10 KSI at 28 days and ultra high performance concrete with a 28-day compressive strength of 20 KSI. Ultra high performance concrete is growing in use in transportation applications due to its very high compressive strength and also for its relatively high tensile strength because of the fibers that are added. It also flows very well. So it's easy to place in that annular space. And that's also why we were investigating the self-consolidating concrete, which flows under its own weight. So if we place materials in that annular space, concrete types that you simply just have to pour in, there's no vibration, then it's less costly and it's easier to do. You don't have to worry about vibrating it in a somewhat confined space. You don't have to do that extra cost. Oh, one more thing before I go on. That specimen, in terms of our actual specimen design, our base is 30 inches tall, 40 inches wide, and 50 inches in length, and is a reinforced concrete base. Now, at Fear's lab, we have a strong floor where we do a lot of our testing, but we do not have a strong wall, which a lot of times you use a strong wall to push horizontally when you're testing columns. We don't have that. So we actually have to lay the column over on its side and design a test frame that attaches to our strong floor in order to test these columns. And we had to design and build a unique one-of-a-kind test frame. And that would not have happened without the help of our lab manager, John Bullock, shown on the left, who is not only incredibly ingenious and very knowledgeable about construction, he's also a certified welder. And my master's student, Jackson Milner, on the right, who together, the two of them, did an amazing job fabricating this test frame. So not only did they have to drill over 200 holes for the high strength bolts, there was over 400 feet, or nearly 400 feet of welding, both for the main steel members, which were done W24 by 68, and all of the braces and connections. And then here you can see the steel frame in place, bolted down to our strong floor at Fear's lab. The steel was donated primarily from W&W Steel and helped us bring this project to fruition. We ordered the FRP tubes, which are 7 feet in total length, because again, they run from the top of the footing to the underside of the loading stub. And then the steel tubes are on the right. They are 11 feet long, because they are embedded 2 feet into the concrete base and 2 feet into the loading stub. Now that's actually more than the minimum embedment required for these columns based on the testing done to date, but we wanted to make sure that we did not have a pull-out failure for the columns. We wanted the material to fail in flexure and axial load. And we have a separate task as part of this research project that is investigating different depths of embedments and ways to embed the steel, including ways to do a precast column prefabricated column that is actually installed into the foundation. And here we have the reinforcement for the base of the column, so a reinforced concrete base. And that's placed into the formwork. The white tubes in the formwork are to provide holes for high strength steel rods that are going to bolt the column base to the steel frame. Place the cage into the frame, into the formwork, place the steel into the formwork at the right depth, location, and making sure that it's vertical. And you can see on the left picture, it's held in place by a couple of angles cantilevering off of one of our steel columns. Because of the large amount of concrete here, we could not mix this in the lab. So we had it ready mixed from Delisi, who is a wonderful partner in this project, of donated materials, whether it's ready mixed concrete or the raw materials for the concretes. And here we're placing it into the form. On the left are 4 of the column bases with the steel tubes already in place and cured. And on the right, we are installing strain gauges on the steel tube. We installed a series of 8 strain gauges, 4 in each row at the cardinal points of the steel frame to measure strains in the longitudinal direction. The first row is at 3 inches above the column base, and the second row is at 9 inches above the column base. And you can see one of the strain gauges on the right. Once the strain gauges were in place, we could lower the FRP tube into place. Now you can just use spacers to get the FRP tube centered about the steel tube, because the steel tube is locked in place now after the base foundation cures. And just spacers, the right depth spacers, can hold the FRP tube in place. But to make sure that it was anchored well, we also developed a halo system on the top and tied it down with some ratchet straps to get ready for placing the concrete in the core. So this is one of the SCC columns with the concrete being placed with a chute that we fabricated to lower the concrete from our concrete bucket into that annular space. This is a self-consolidating concrete. It flowed very well. It had about a 26 to 28 inch spread. It consisted of 3/8 inch maximum aggregate because of the only 2 3/4 inch thickness of the concrete. We didn't want to use a larger aggregate. And it flowed very well with no vibration, no external vibration or internal vibration, and filled up that annular space extremely well. And then here we have one of the FRP columns, our UHPC columns, placing that again with the same chute. It flows under its own rate. For those of you familiar with UHPC, it's a very unusual concrete. It only has cementitious materials and sand and an awful lot of high range water reducers. It's very flowable, but it's also very sticky. It tends to stick together. It's kind of like, I'm probably dating myself, but it's like Nickelodeon slime, except instead of being green, it's actually a dark gray, almost black. And it flows extremely well and fills up that 7 foot tall column with no external vibration and completely fills that annular space. We also designed and constructed a reinforced concrete column with a nominal 18 inch diameter. The reason we wanted to do that, even though these columns have been tested to death, is because we wanted to make sure that our testing system and our loading protocol gave us the right kind of response before we put in these new columns, our HCFCS columns. So it's an 18 inch nominal diameter using a sonotube for the form. There are 8 number 6 bars for a reinforcement, longitudinal reinforcement ratio of about 1.3%. Now, we didn't know exactly what the flexural resistance of our HCFCS columns were going to be, so we weren't trying to match that. We were just trying to come up with something close to, again, make sure that our loading system was correct and our loading protocol was correct. We also installed strain gauges on the longitudinal steel at the same location we installed strain gauges on the steel tube for the HCFCS column. And there you see the completed concrete column on the right. Now, unfortunately, we only have a 5-ton overhead crane in our lab. And if we were to cast the loading stub on top of our column, they would weigh more than 10,000 pounds and we wouldn't be able to move them around the lab. So we actually had to tip the columns over, move them into the test frame, anchor them to the test frame, and then fabricate the reinforcing cage and the formwork to install the loading stub. And here you see one of the loading stubs before the concrete has been placed on the left. You see the steel tube extending 2 feet into that loading stub. And then you see the finished concrete loading stub on the right. And the black is just plastic to protect the existing column and the loading beam. And then here we have a completed column within our test frame. Of course, we've got the test frame painted a nice OU crimson. We had a few bugs at the beginning of our testing. We had to refine the test setup a little, and that's because this is a unique test frame, a one-of-a-kind test frame. So we made some refinements on it. So here you see the base anchored to the frame through 8 high-strength threaded rods. They go through the concrete, through those PVC tubes that were in the formwork that you saw, and they penetrate through the W24x68 flanges and then are anchored on the backside. This is our hydraulic ram. It has about a 26-inch stroke, so it is showing extended halfway because we push on the column in one direction, pull it back to 0, and then pull it back the same distance in the other direction. And then here we have our load cell protected to make sure everything stays in alignment. These are the wires that come out for the strain gauges that are on the steel tube. We also have strain gauges installed to measure the hoop stress in the FRP tubes. You can barely see them. These are these little silver dots right here. And we have those to measure the hoop strain that the FRP tube is experiencing. On the backside of the loading stub at the same location as the ram, we have wire pot to measure the displacement of the top of the column. We have another wire pot on the other side of the column at about mid-height. We also have 2 wire pots on the back side of the base of the specimen in order to measure any rotation in the base. Even though we designed the test fixture in terms of both strength and stiffness, it's not infinitely stiff. Those steel girders are going to deform, and so that base is going to rotate a little bit. And if you just extend that out as a straight line, that's going to cause lateral displacement of the loading stub. And we need to subtract that out of the displacement that's being measured with the wire pot to get a true estimation of the displacement of the top of the column relative to a truly fixed base. Now, again, we have our diagram of the column on the right. And on the left is our testing protocol. This is based on a FEMA standard. It is a standard protocol that was used on all of that column testing that I showed you previously, the hollow core and the steel and FRP filled concrete cores. And that loading protocol is you start with an initial displacement. You push the column in one direction for that displacement. This is all a displacement controlled test as opposed to a load controlled test. So you displace it by that amount. You pull it back to 0, and then you pull it in the other direction, the same amount, push it back to 0, and then do a second cycle at that same displacement. Then the next cycle is done at a 40% higher displacement. 2 cycles of that, 40% increase, 40% increase. So the displacements are increasing exponentially, and that's shown in the diagram on the left. Based on calculations, we wanted to make sure that we didn't push it too far for the initial displacement, but we wouldn't want too small of a displacement or it would take forever to run the test. And so we arrived at a displacement of 0.05 inches or 0.05 of an inch for the initial displacement. And that was expected to give us a lateral load or require a lateral load of about 2,000 to 2,500 pounds to get to that displacement. So that was our starting point. Our ending point was a displacement of almost 11 inches, the 10.89 inches. And all of the columns we failed before or when we got to that point. So I now want to talk about the load displacement response. Just like those load displacement response I showed you for the hollow core concrete columns and the concrete filled steel and FRP columns, we want to look at the same behavior, because when you come up with a new structural system, a new structural element, right? Civil engineers, and I'm one of them, particularly structural engineers, we're a conservative bunch. We want people to show us how these new things are going to work before we start putting them in our bridges that people are going to go over, right? And so we want to test them the same way and see how they respond so we can compare to them, so we can develop a level of comfort that will leave the public in a safe situation. So here we have the load displacement response. Before I actually show you the response, I want to talk about what this is showing. The vertical scale is the lateral load in kips. So 10, 20, 30, 40, 50 kips, both in one direction, a positive direction and a negative direction. So when we push and then when we pull. And then the displacement is on the horizontal axis, 5, 10, 15 inches, both pushing and then pulling. So first, we wanted to look at the behavior of our reinforced concrete column. And that again was so that we could feel comfortable with the response, so that we would indeed feel comfortable doing these new columns, because this test fixture is unique. And so if you look at the behavior of it, it performed as a typical reinforced concrete column. You have initial linear elastic response when the deflections are low. All the materials, the steel and the concrete, are behaving linearly elastically, which is great, which is exactly what it should do. At some point, you begin to crack the concrete in tension. And because it's a cyclic loading where you go in both directions, you're going to crack it on one side that's in tension, and you're going to crack it on the other side when you reverse the load. So eventually you start to become nonlinear once you crack the concrete. The other thing is you have a cold joint between the concrete and the column base, which is typical of construction. You're going to have a cold joint there, which is okay because we don't count on the tension capacity of concrete in our capacities. So whether it's a crack that forms or it's a cold joint, that's what the reinforcing is for. But the concrete starts to become nonlinear once you start exceeding about 40% of the ultimate compressive strain, and the steel bars start to become nonlinear. So eventually you start yielding the bars. Remember, this is a circular column. So you're going to start to yield the bars that are farthest from the neutral axis first. Once those start to yield and go through additional strain, you're going to start to yield the bars that are closer to the neutral axis, closer and closer. And you see we have increasing displacement. We have a nice hysteresis loop. It's fairly stable initially, but then at some point you get this little dip here and these dips here. What happens here is because of the high strains, we most likely either buckled a bar or fractured a bar due to the strains getting too high. And that's why there's a dip in capacity, but there are 8 bars in there and the other bars start picking up the load and we get a continual hysteresis loop, but at a much lower load. So much lower in terms of the lateral load, also much lower in terms of the energy absorption. And this is very common of a reinforced concrete column tested in this type of protocol. So we felt very comfortable that our test frame and our test protocol was indeed doing the things that we needed it to do. So then we moved on to the SCC column, shown in this next load displacement plot. Now you can see here, we get, as we did with the reinforced concrete column, you get a linear elastic response. The steel tube and the concrete are acting nice and linear elastically. At some point, we're not sure you're going to debond that concrete core from the base. We're also starting to get some nonlinear behavior. That may be nonlinear behavior because, remember, again, we have a steel tube, a circular steel tube. So you're going to start, just like the reinforced concrete column, you're going to start to yield the material farthest from the neutral axis. So you're going to start to yield the steel tube at the tip. And then that plastic zone is going to grow as you plasticize the cross section. And of course, you're getting a nonlinear response because for part of the cross section of the steel tube, you're in the plateau region, which is inelastic and absorbing energy. But part of the steel tube closer to the neutral axis is still behaving linear elastically. So you have a combination of two. But we're talking about putting very, very high strains on here, okay, up to 10%, right? We have an 8-foot tall column, so 96 inches, with it's going to a displacement of over 10 inches would give us over a 10% drift ratio or ductility factor. So it's very high displacement. But here we see we have a nice stable stress strain response, nice stable hysteresis loop, but then something funny happens in here. And you see in these later cycles, we have this dip. What's happening here is, remember, we have that steel tube. which has a tendency to buckle locally. The concrete core is providing resistance to that steel tube. And we'll talk more about it, how it actually provides that resistance and the particular mechanics of it later. But just realize that at some point, that steel tube at the extreme fibers is going to experience a high enough strain that it wants to buckle locally. And that is what's happening here. So if you look at, let's say, the very last cycle, you see the capacity is very low here. What's happened is we've buckled the part of the tube that's in compression. So when we were placing it in compression over here, it buckled, and then we started to go back in the other direction. Now, what happens is, so here it's in compression, we bring it back to zero, we start putting that buckled section of the steel tube into tension. What happens when you place that buckled section of the tube in tension? It wants to straighten out. Then you start having an increase in capacity. So that wrinkled, if you will, steel tube is now stretching out when it's in tension, and then you continue to increase in capacity because the steel tube is still there, and in tension, it's not buckled anymore. But then you go back in the other direction, right? You start reversing the flow and you come back in the other direction. And again, you buckle the steel tube that's now in compression, and you start to straighten out the other opposite side of the steel tube and pick up load. So very good stress strain response, very load deflection response, nice, fairly consistent in the beginning, non-deteriorating response, non-deteriorating hysteresis loop, a lot of area in here to absorb a lot of energy. And that's good for these multi-hazards, which are dynamic in nature. And if you can absorb the energy, you lower the effective loads that's acting on the element. Oh, before I do that, then we ended up having a peak of about 43 kips for the maximum lateral load. And it's important to also see that there was degradation in the peak for the SCC column. Not a lot. We get down to about 40 kips, maybe 39 kips, but there was some degradation. The UHPC column, which is identical to the SCC column in terms of the steel tube and the FRP tube, the only difference is the concrete. The SCC has a compressive strength of 10 KSI. The UHPC has a compressive strength of 20 KSI, but also has steel fibers, which increase the tension capacity. So it's going to provide better confinement. It's also going to take some tension. And it showed this by not having a deteriorating stress strain diagram. So initially, linear elastic, just like the RC column, just like the SCC column. Eventually, we start getting some inelastic response. We start to yield part of the steel tubes at the extreme fiber, but we're still increasing load. Additional cycles, we're still increasing load, We get up to about 49 kips. So we've got an almost 14% increase over the SCC column with the UHPC, which is more than statistically significant. So it's a noticeable increase. And we have a bit more, therefore, area under our stress strain, our load deflection response, more energy absorption. We do still get buckling eventually of the steel tube. And again, when that reverses and the buckle comes out, you start picking up capacity. And we only get a decrease from about 49 to about 42 kips with the steel tube buckling. Now, eventually, if we were to cycle this thing back and forth up to that almost 11-inch displacement, that steel tube is going to fracture. It's like when you take a paper clip and bend it back and forth and back and forth and back and forth, right? That's what's called low cycle fatigue, high stress, low number of cycles. Eventually, you would fracture that steel tube. But for this application, it's going to buckle locally and then straighten out. So it has not completely failed in terms of resisting the lateral loads on. You certainly wouldn't want to leave it like that after the earthquake is over. You don't want to inspect it and make sure it's okay if you were to have a high seismic result, but it has a lot of reserve capacity. It has a lot of resilience, which is important for structures subjected to multiple hazards. And then here's an overlay of the SCC, which is this plot for those of us who are colorblind, this blue plot. And then this orange plot is the UHPC, and you can see the difference in behavior. So again, the SCC started to decrease in capacity a little quicker, Earlier on in the cycles, the UHPC was still picking up peak load and decreased just a little bit before the very last cycle. So it's going to absorb more energy. So again, the important thing is to recognize that the only difference between these two specimens is the core concrete. The UHPC apparently provided more capacity, perhaps more buckling resistance to the steel tube, because the longer you can go before that steel tube buckles, if you can fully yield that cross section, reach the plastic moment capacity of that steel tube, you're optimizing that material. It can't get any better than that. That's the ultimate goal. If it buckles, you're not using the material as efficiently. And then here is an overlay of all three. This yellow plot is the reinforced concrete column. The blue again is the SCC column, and the orange is the UHPC column. Now, once we ran the test, we of course observed them during the test when you can learn a lot. And we also did forensic examination when the test was over. So here we have the reinforced concrete column. Typically, when we test reinforced concrete columns in this manner, we will paint them white with a combination of white paint and water, so to make the cracks more evident during the testing. So here you've got the column ready for testing. We started to cycle it. On the left are some of the initial cycles. Those black lines on the column are cracks in the concrete, right? The concrete is weak in tension. It's going to crack in tension. Since we're pushing it and pulling it in both directions, you're going to get cracks on both sides, so you get these transverse cracks. Nice spacing on the cracks, about 6 inches on center. Great behavior. On the right is where we've increased the cycles even more. We get more cracking, and what typically happens in a test like this for reinforced concrete, you start to spall the cover off because there's nothing holding the cover on other than tensile strength of the cover bonded to the concrete on the inside. So it's very typical to start spalling off the concrete. On the left, more cycles. You can't see it very well, but here we've actually fractured this bar, which is the bar that's farthest away from the neutral axis. It happened to fracture very near where we had a strain gauge on it, so you can't see it very well. These two bars are still okay. More cycles for the picture on the right. You can see that we've now buckled that top bar and we've buckled that bottom bar. And there you can see a close-up. Again, we've buckled this top bar, even though the spiral is there to prevent buckling, the concrete is there to prevent buckling. But as you put higher and higher cycles, you're going to start to rubbleize the concrete in the core. And so it provides less and less resistance to the longitudinal bars buckling. And then on the other side of the column, it suffered the same type of damage. Here you can see this bar on the top, looks like it was sliced through with a, like a knife through butter. It goes with the crack in the concrete, but this is fractured. This bar is fractured. This bar is fractured. And, which is not uncommon, this bar down here is pristine, still carrying load. Just, because nothing is perfectly symmetrical. So that's the behavior of the reinforced concrete column, very typical. Then we look at the FRP column. First, the SCC filled FRP steel column. Now, unlike the reinforced concrete, you can hear this thing going through damage, but you can't see it because of the FRP on the outside. So the only thing you can see is how the FRP is performing. And you can see in the picture on the left, this is the column pushed all the way over 11 inches. And again, we went in both directions. So a total displacement of 22 inches. At the bottom of it, where the FRP comes in contact with the concrete base, you see some white there. If you see a close-up on the right, you can see that this white is where the FRP has started to split. And here it's actually fractured. These are the strain gauges measuring the hoop strain in the FRP during testing. And here, the compression has gotten so high on the concrete that we've exceeded that 40 KSI hoop stress for the FRP. We then longitudinally or circumferentially cut the FRP and then slice it longitudinally to peel it off and to look at the concrete underneath. And here you can see the concrete underneath was confined very well. You can see it's in much better shape than the concrete for the reinforced concrete column, right? There's a lot of cracking, right? There's some spalling, and the concrete has started to break up into pieces, but it's fairly well intact. So that FRP is providing a significant amount of confinement. And again, this is at a ductility ratio of over 10%, almost 11%. That's a lot of displacement, right? That's 22 inches of displacement for a 96-inch tall column. Then we remove the concrete. We had jackhammer the concrete to get it out. And we start looking at the steel tube. The steel tube from one side on the right and the other side from the left. And you can obviously see where it has buckled. Buckled here, it's buckled here on the other side, buckled closer to it, and here. Now, the important thing is understanding this buckling, because I talked about the fact that the concrete core provides buckling resistance for the steel tube. At first, you kind of scratch your head and go, yeah, but it's hollow on the inside. It can buckle inward. The concrete's only going to keep it from buckling outward. That's true, but if you think of this steel, if you take a strip of this steel, similar to a ring that you put on your finger, right? It can't buckle everywhere inward. If it were to, in order to do that, you would place a hoop compression string because you're trying to push material into a smaller diameter. If you test steel tubes under compression, if you've looked at any other testing, you'll see when they buckle both inward and outward and not in the same location. So they might buckle inward on the two opposite sides and outward on the other two opposite sides. That's the least energy state. But that concrete is confining it. So you get really a three-dimensional buckling state. This is how the concrete confines the steel from buckling. That is at a much higher energy state, much more capacity. Then we get to the UHPC column, same kind of thing. You can hear it breaking, but you can't see it. Here's the column pushed all the way over. Here, the FRP has not split as much at the same displacement, the same cycling. That might be because the UHPC is providing more confinement. And then when we cut the FRP away, you can see that the UHPC is in phenomenal shape. There is cracking. There is some more cracking here, but you really have to look hard to find it. And there is literally no spalling. It is staying fairly intact. You excavate that out of the way and you look at the tube and you get the same kind of response. We get buckling of the tube. That's more of a three-dimensional nature. And if we look down at the tube from the top, again, you can see this more three-dimensional nature of buckling the tube, most of it buckling inward, but at different locations. In terms of our next steps for this research project, we're going to look at reducing the thickness of the concrete core and using the same steel tube, smaller diameter, same thickness FRP tube. We're going to go from 18 inches down to nominal 16-inch diameter. We're also going to look at the potential for increasing the steel tube thickness a little bit to see how that helps in terms of adding capacity. We're also examining in another task the development length, how far we have to embed the steel tube into the foundation and into the pier cap to fully develop it. I'd like to big thank you to the Oklahoma Department of Transportation for funding this research, in particular, Walt Peters, Gary Hook, and Ron Kerb. I'd like to thank the ABC-UTC at Florida International for funding a companion project to the ODOT project. And I'd like to thank the Southern Plains Transportation Institute for sponsoring this webinar. DeLisi, who have donated a lot of raw materials, aggregate, cement, and fly ash, and ready-mix concrete when we didn't have the capacity to mix enough of it. To Grace Composites, who donated the FRP tubes, W&W Steel for donating most of the steel for our test frame. I'd like to thank my co-investigator, my research colleague, Royce Floyd, my master student, Jackson Milner, John Bullock, the FEARS Lab lab manager. Again, a big shout out to Jackson and John. This project would not have been possible. And just give you an idea, for those of you who are not familiar with FEARS Lab, it's in an unair conditioned steel box. And these guys had to do welding in the middle of last summer. So they came in at 2 o'clock in the morning when it was cooler to do a lot of the fabrication. That's going above and beyond. Omar Yadek, who is a master student for Royce, who is working on the other task in terms of embedment into the column, of the column into the base, and also helping with the fabrication of our column tests. To Chris Ramsayer for helping with W&W for the donation of most of the steel for the test frame, and for lending us his big actuator and hydraulics to run the test. Scott Harvey for donating a laptop to us and helping with our LabVIEW software to get it to run. And Jake Choate, another of my master students who helped out. With that, I would like to answer any questions you might have.
Wonderful, Jeff. Very, very stimulating presentations. So we really appreciate, and also we have a large number of people listening, to your presentations. There are several questions that are posted. Maybe if you can probably stop sharing the slide, or I don't know, maybe questions you may have to actually go to some of the slides. So I think let's keep the slides. So I will actually go in the order that we have received these questions, and then perhaps you can address. So there are a number of them. So one question is that when we fiber wrap existing columns, they always have us leave gaps so the concrete can breathe. You are not providing, are you providing any gaps? And how do you address these concerns?
We are not providing any gap. We would not get the confinement of the concrete if there were a gap. So it's poured up flush to the FRP. And I agree, it is an issue that has come up with combining FRP with concrete or FRP with concrete and steel. Is the nice thing about steel and reinforced concrete is it's easy to inspect. Once you start wrapping things with FRP, it gets harder to inspect. And there are issues with moisture. So it is not a perfect system. And that is something, as this technology evolves, because it's still very young, ways to inspect these columns needs to be developed. So it's an excellent question and one we definitely struggle with.
Wonderful, thank you. So the next question is, how does the contractor center steel tube in the FRP outer column? That's also important question in terms of application.
Yeah, so okay, so both the steel, so centering the FRP around the steel, did I get that right?
Yeah.
Okay. The best way we have found, it turned out very well that if you you can get those round bar ties, bar positioners, and if you get the right size, and you basically have to have a spacer between the steel tube and the FRP tube, and it would most likely, unless you're lucky, have to be specially made. Again, you could make that out of FRP, and you could even 3D print them, but you basically want a spacer of a set amount that's the thickness of the steel tube that you can, thickness of the concrete that you can place against the steel tube, so that you can position the FRP tubes concentrically with the steel tube. So yes, definitely, it's one of those construction details that definitely needs to be worked out in no pun intended, more detail. But it would be similar to bar chairs for reinforcement within a reinforced concrete column or a reinforced concrete beam, right? How do you get the steel at the right location? We use chairs of different dimensions to get them to the right location. But it is important, because if it's not centered, it's not fabricated correctly.
So Jeff, would you put that the spacer at different locations, height-wise?
Yes, depending on how high that FRP is, you would need multiple ones of them to get the right location and those spacers. And that's kind of would come with feel as we develop this technology, how many you need, how frequently you need to have them, just as we develop a feel for how many chairs we need to support our reinforcing cages. You don't want to put in too many, but if you don't have enough, the steel sags between it and can potentially get displaced, which can cause problems. Same as positioning a steel duct in a post-tension concrete application. You have to locate that and physically restrain it while you place the concrete. So these would be things that we've experienced in different types of construction. So I don't think it would be too far out there, but it would definitely take some thought.
So the next question, I think, is kind of more of a clarification question that, you have presented in your graph displacement versus load. So the audience wants to make sure which axis is displacement and which axis is load. So I think if you clarify that, that would be great.
Yeah, this is one of the drawbacks. I don't want to blame Excel, but the vertical axis is load, even though it puts the label right below that axis. That's the label for the horizontal axis. It's just a quirk of Excel. So the vertical axis is lateral load, 10, 20, 30, 40, 50 kips. The horizontal axis is displacement. So yeah, the first time we plotted those, I was like, that's not right. So I feel your pain.
Yeah, I thought the same way too, because normally that's how we are used to seeing. The next question is that it is there, what is the actual capacity, the load capacity? Is it 49 kips or something else?
Good question. We calculated a capacity of these columns at about 42 kips. Now that was for kind of an average compressor strength of 15,000 psi, sort of middle of the range. This was just more to get us a feel. So it behaved very close to what we calculated with our nonlinear strain compatibility analysis. So fairly close to it. And you're right. Eventually, it would be actually better to, or another way of displacing this information would show the plots where the vertical scale is a function of the static capacity. So it's often showed like that.
Excellent one. Then the next question is, how much vertical load was applied and how was it calculated for these tests?
Great question. Based on previous research, we wanted to apply between 5 and 10% of the axial capacity of the column to the column. So it's a relatively small axial load. And it was actually based on the reinforced concrete column. And we applied 5% of that load and we kept it the same for all of them. And if you think of an interaction diagram for reinforced concrete, you know how it's kind of got a, I don't know what that shape is. Not quite a bell shape, but at low axial loads, as you increase the axial load, you actually increase the flexural resistance until you hit the balance condition, and then additional axial load will decrease the lateral or the flexural resistance. So typically, most of our bridge piers are in this lower range. So in this case, more axial load, if we put more axial load on the column, we'd actually increase the flexural capacity. So we wanted to have a relatively low axial load. And this is very consistent based on previous research, is that's where they target that amount.
Wonderful, very good explanation. So the next question is, will the contractors be able to attach or hang the cap forms to the columns as they normally do in case of reinforced concrete columns?
Yes, absolutely. Once you place the concrete in the core between the steel and the FRP, it's got all of its capacity. It would, designed essentially to be a cantilever, and so it's at its, as soon as as the concrete gains strength over time, it will get more and more. But once you place the concrete in the core, letting it cure for a couple of days, you could put a significant amount of load on it. It's ready to go.
Excellent. So what's the rough difference in cost between these two options that you discussed?
Great question. Depending on the actual design, it can vary. The cost depends on the concrete you put in the core, right? Ultra high performance concrete is a very specialty concrete. It's expensive. If you use proprietary products, they can run up to $1,000 a yard, which is excessive compared to regular concrete, which is $100 a yard. Non-proprietary ultra high performance concretes can be less expensive, so that's going to control the cost. The steel tube, depending on the design, can be fairly close in terms, usually a little bit higher than the steel tube, than the reinforced concrete longitudinal bars. And then you have the issues, the problem is, I know I'm dancing around it, and they are relatively close in cost if you start including things like the cost of formwork and the time. They become fairly close in cost, and it really just depends on the final design and how much the contractor can automate it and get comfortable with the system. And then you start including things like the indirect costs due to accelerating the construction, and it can get very complicated. But they are the same order of magnitude. If you start including a lot of those indirect things, they can become more cost effective. But if you look to some of the base material costs, they're close. It includes things like formwork and the time it takes to build fabricate a reinforcing cage, both to bend the bars and to tie it together on site. That's where you start to see some of the savings where you might have somewhat higher material costs.
Yeah, and I guess also as you become more familiar or use them more, the cost would come down as well, right?
Excellent point. Yes.
The next question is, how is corrosion eliminated for the steel tube from inside?
That is it. That is an excellent question, and a question I've gotten a couple of times. And so, it's a confined area, right? Now we're looking at using bare steel because we want to get the best bond with the concrete. Because you remember, the concrete is going to fill up the inside of the tube up to the top of the foundation, and the inside of the tube down to the bottom of the pier cap. You have to put a plug in there to stop it from filling it up. But now it's a confined space. It's an enclosed space that has air in it, and that air is going to have humidity in it. And as the column gets cold, that humidity is called condensation, and you're going to have moisture and oxygen on that steel. It's going to slow down corrosion because you don't have an unlimited amount of oxygen, which you need for corrosion. But it would probably be a good idea to put a primer on the inside of the steel tube where it's not within the concrete foundation or within the pier cap, to ensure that you don't have any corrosion, because unless you have an access hole with a fiber optic camera, there's no way to inspect it to find out if you are having corrosion.
Absolutely. The next question is also important one. What are the implications of these new technologies? You talked about the column, to foundation design of the foundation itself.
Oh, good question. We have somewhat lower dead load from the self weight of the column, but not much compared to the weight of the superstructure. That's going to make a difference. In terms of the forces that are transferred to it, and that's one of our tasks in our research project, is how far do we need to embed the steel tube into the foundation to fully develop it, just like you have to figure out how far to embed reinforcing steel in a reinforced concrete column. But then the loads that you're going to impart on the foundation would be identical to the loads that you're going to impart from a reinforced concrete column cantilevering out of the foundation based on the response of the structure. It would be the same types of forces, provided you embed the steel deep enough, just like we would do the longitudinal reinforcing bars of an RC column. You're going to get the same types of forces that you would with their circular reinforced concrete column.
So I think the next one is also kind of, so this is there any particular reason for the thicknesses and the dimensions that you selected for your testing?
Yes, we went by those current design guidelines, these initial ones, which let me jump back to this. These initial sizing guidelines, which again give you a start. Once but you have to pick an exterior diameter. Yeah, that has to be your starting point. So again, in an actual column, you could use the same roughly sized diameters as you would have selected for a reinforced concrete column as a starting point. And then from there, you follow these guidelines. They give you the thickness range for the concrete, the diameter and thickness range for the steel tube, and of course the diameter and the thickness range for the FRP tube. Excuse me. And again, those ratios for the steel tube, the 1/64th at the lower end, that'll give you the thinnest. Then you're going to have a tendency for a little more potential for buckling. As you make it thicker, you'll have less buckling at the 1/32nd. And then if you're in a high seismic region, you're going to want that thicker FRP thickness because you're going to have much higher strains. That's the big thing about seismic. It isn't necessarily that the forces are higher than you would from perhaps some other type of vehicular loading or something else. The strains are so high because the displacements are so high. So those strains, you're going to have a thicker FRP because you're going to have much higher compressive strains in that concrete core, and it's going to want to expand because of Poisson's effect, and that's how the FRP restrains the concrete.
Excellent.
So these are good starting points, but again, then you want to do a more detailed analysis.
Yeah, next one is also a very interesting question, that it appears that a failure occurs at the connections, or near the connection. So with this in mind, is the steel tube really making much difference in the middle of the column?
Yes, no, excellent question. I mean, because most of these bridge columns are essentially flagpoles, right? They cantilever from the foundation, and they're going to move based on the forces that are imparted from the superstructure. And even a reinforced concrete column, a steel column, you're going to form that plastic hinge at the base. If you wanted the most efficient column, you could do a tapered column, but then you have the fabrication cost of that. You could change the thickness of the steel tube, but again, there's a fabrication cost in that. So yes, in terms of when you get to the excessively high stresses, you're going to form that plastic hinge at the base, just like you would with a reinforced concrete column or a steel column. And yes, a tapered column of some type would be more efficient. Maybe perhaps, the technology would exist to use a tapered steel tube that gets narrower at the top, and then it's a more efficient use of the material. So excellent question, because you're right. You look at the fabrication of this column and you're putting it in the test step and all the effort, and you break it right at the base. And the rest of the column looks perfectly fine. And it's unfortunately just the nature of the beast.
Yes, and also perhaps the 3D printing, Jeff, going forward.
Yeah. Oh, excellent point. Excellent point. And additive manufacturing for the steel, we could make a much more efficient. Because one of the ideas we're also investigating is when we're looking at the embedment into the foundation is you could prefabricate these off-site and have a splice connection to the foundation. And then if you automated that in a factory, you could really refine the design to be more efficient with additive manufacturing and 3D printing. Excellent point.
Last question. Is there any way to inspect the condition of your column from inside?
You would have to place holes, access ports, access holes in the column so that you could install a fiber optic cable, fiber optic column, kind of what they do to inspect the inside of sewer pipe or water pipes, where they place the fiber optic cable inside with a little camera. But you could place an access port. It'd be a nice way. You just have to have the fiber optic cable and the camera to put it in there and to run it up and down the column and to look at it, just like you would inspect pipes that are buried in the ground.
So I think Dr. Volz has done a wonderful, wonderful job, not only clearly presenting this difficult topic. We do this pretty frequently. We have done it many times, Jeff, but we have not seen as many questions as we have this time around. So everyone, and we also had very large number of participant attendance. So everyone, would you please give a virtual applause to Professor Jeff Volz? So with that, you will have a copy of the presentation PDF on our website, and also wanted to let you know that we have recorded this presentation. So you want to listen to this again, and the audience greatly appreciate what you have done, Jeff. We are very thankful to you for taking your time out of busy schedule, and we had a wonderful audience, participants. Without your participation, we would not have an event. So thanks to all of you, and we'll have another. I think our goal is to do this in a fairly regular basis. So thanks to all of you for your time and your participation. All the best. Thank you. And your PDH will be, you should receive your PDH because we have a list of participants. So thank you so much again, and we look forward to seeing you again.
And thank you, Mushraf, for the opportunity. I appreciate this, and a big thank you to all the audience for being interested in what I can often think of as a nerdy structural engineering problem. So,
excellent. Thank you. Thank you.
Thanks.